Gabor Furesz, if I got that reasonably close, is from MIT's Keck Institute of Astrophysics and Space Research. I didn't get in there. We met him at Cellophane. I wasn't there, but Dan met him at Cellophane last year where he took the photo that you saw. And he's here to tell us about big telescopes. So please welcome Gabor.
Thanks for coming, despite the impending snow Magellan or whatever it is. 6 inches of snow tomorrow, and sorry about the last week, but the last week was actually really bad, so I couldn't make it. So thanks for coming, and I will try to talk within an hour. I sometimes have a hard time keeping that, but if you're bored, just let me know and move faster. So what I will talk about is telescopes, just because you have enough of them, but never, big enough, I guess. We always wish for bigger telescopes. And so scientists now are building these, 30-meter across kind of telescopes, one of which is in this front image. And so I will talk about not just these next generation of telescopes, but how we got there. So a little bit about the history of telescopes themselves. And of course, we'll look at some of the current largest telescopes. We'll pay tribute to the very famous 100-inch Mmt Telescope on the way, because it was 100 years old last year. And we'll talk about little telescopes and some space telescopes as well. We'll see if I can fit it in there. So let's get going. So astronomy, as you know, is one of the oldest science out there. And I like to think of these big telescopes as like cyclopses, because they are one big eyes looking at the sky. And so astronomy dates back to those mythical creatures, or even before. And so astronomical observations for a really, really long time have been only carried out by the naked eye, not with the aid of a telescope. It's only the last 400 years when, after Galileo, we all turned telescopes towards the night sky, and man, did they have a big impact. So when Galileo had his own telescope, it was only 2 inches in diameter, but even with that, he made groundbreaking discoveries, which led to essentially abandoning the geocentric universe. He could show that little things move around Jupiter, which you know now as the Galilean moons. And of course, people started to think about, so why don't we build bigger telescopes and see better? And there was William Herschel, and he was almost 200 years later building a 20-inch telescope. So I look at these telescopes and 20 inches is not a big deal, not a big deal today, but then it was. And it led Herschel to realize that actually the Milky Way is sort of a bunch of stars. He was counting star density in different directions and figured out that the Milky Way must be some sort of group of stars. Or, go ahead in time another 150 years and arrive to the famous 100-inch telescope, which we'll talk about. And that 100-inch telescope led the discovery of variable stars in other galaxies. We didn't know back then what galaxies are, and we thought those are just like little smudges in our backyard. We didn't quite appreciate how distant those galaxies are until it was measured by the 100-inch telescope. So the point here is to take away is that every time a bigger telescope was made, groundbreaking discoveries were the result. And so that's the motivating force, spending billions of dollars on ever bigger telescopes. And we'll talk about that. But so as we talk about the evolution of a telescope, and I'm going to talk about these giant telescopes, I'm going to show you, I'm not too proud of the picture, but that's me. And so I had my own evolution of telescopes. When I was 12, I started with that. I'm particularly proud of that mount. As you can see, it's a Weiss, and it's an aluminum tube. It's like a 4-inch little Newtonian that my father and I built. But then 15 years later, I went to 6.5-meter telescopes, where I was mostly using them, but also building instruments for them. I have a degree from astrophysics, but I'm more on the engineering side, so I design optics and build spectrographs and cameras and the like. This is the Mmt Telescope, which is used to be the multi-mirror telescope. Now it's called the monolithic mirror telescope. So they didn't have to change the name. Used their 6 1.5 meter mirrors, and they replaced it with the 6.5 meter mirrors. We'll talk about how these big mirrors are being made today. But now let's talk about the evolution of the telescopes in general. So here you see a timeline from Galileo's very, very small telescope, which was very small in diameter. The vertical axis is diameter in meters, so in yards. Sorry, I'm from Europe. I do meters. At least the years we agree on, so the years are years. And so you can see that over time, the diameter of these telescopes got larger and larger. And you can see that these symbols are all little blue squares, and now here comes a red circle. This red circle is indicating a different type of telescope. So these are the reflectors, which were introduced by Newton. And then you can see that these days the red circles took over the blue squares. I have no political intention using blue and red. Okay, so just going to put it up front. It's not a political prediction. It's just a graph about telescopes. So let's not get into it. And so you can see that the refractors, the lens-based telescopes, stopped in 1900 essentially. But then the size of these reflectors, the mirror-based telescopes, they just went on and on and on. And you can see that you can actually fit a trend line to that. And so once you do that, the question comes, so can you just project that to the future? Can you really build a 100-meter telescope? Because that line kind of approaches the 100-meter in, sometime soon. And so if you recall, there was a telescope which was called OWL. It's an acronym for Overwhelmingly Large Telescope. It was a European design for a 100-meter telescope, and they were talking about it very seriously. Again, I'm from Europe, so I don't want to joke too much about it, but since that telescope turned out to be a little bit too big, they kind of scaled it down, and it still exists. Now it's called the European Extremely Large Telescope. And so the American colleagues like to joke that actually that acronym was the once was large telescope, not the overwhelmingly large. But anyway, so that telescope still exists. It's called the EELT. It's 39 meter in diameter at the moment. And as you can see, there are two other dots there which are fitting pretty well this line. One is the TMT, which is, guess what, is the 30-meter telescope. And the GMT, which is the Giant Magellan Telescope. And what these telescopes are, roughly compared to each other, that you can see here, compared to the Big Ben. And so the Giant Magellan Telescope is about 26 meter in diameter, but it consists of only 7 mirrors, but large ones, 8.5 meter in diameter each. The 30-meter telescope is 30 meters across. And it's consisted of many, many segmented, little smaller mirrors, which are about 1 meter in diameter. And the European Extremely Large Telescope, which used to be 42, and right now I think it's 39 meter in diameter. Here's a better rendering, computer generated image of the EELT. And in real scale, a Boeing airplane. So you appreciate the size of these things. And so, before we start talking about this next generation of telescopes, I would like to call your attention to a group of telescopes here. Namely, the Yerkes telescope, which is a refractor, it's a lens-based system, but then comes the Mmt Wilson 60-inch, and then the Mmt Wilson 100-inch, and the Palomar 200-inch. Because these telescopes actually had been the largest telescopes in the world at their time. And guess what? All of those 4 telescopes have one man behind that, and that was George Hale. And so, especially these days when funding for any sort of science projects is really, really hard, I think we should really appreciate George Hale's work, who managed to essentially initiate all of those 4 telescopes on his own, basically. He got the seed funding for all of those telescopes. So he essentially built the largest telescope in the world 4 times over, which is quite a feat. The first one that he built was a lens-based telescope, and since I am right now at MIT in Cambridge, actually it's a kind of interesting thing that once the biggest telescope on Earth came from Cambridge, Massachusetts. If you look up the old map of Cambridge from the mid-1800s, you see the city map from the Harvard Library here, and if you look closely there, there's this little three-legged thing with a big thing sticking out of the sky. So even the city map showed something, and that something was the factory of Alban Clark and Sons, who made really, really big lenses. And so the Lick Observatory 32-inch lens, and then later on the Yerkes telescope 40-inch lens came from that little factory of father and two sons. And when it was inaugurated in 1895, that was the largest refractor of all times. It wasn't the largest telescope, it was the largest refractor, and still to date the largest refractor. They built for the Vert exhibition in Paris like a few years later, an even larger one, but that was really horrible. It was not on a mount, it was horizontally located, and then you had like a solostat to put light in it, but it was really not living up to its size. So here you can see the largest lens made for a telescope. And the reason that thing came about is because Hale, who was a really brilliant student, and actually he also went to MIT amongst many places, but he was based from Chicago, and his father was sort of well off and wanted his son to succeed in science, and he did, but he also figured out he has a knack for getting funding. And what happened is that Alban Clark had this large glass blank sitting because the university in California ordered a large telescope, but due to financial problems, they couldn't pay for it. And Alban Clark was like, oh, well, I had this glass blank from Paris, so what I'm going to do with it? And then at that point, the University of Chicago wanted to build a world-class observatory, so George Hale was like, oh, I know what to do, and essentially made the thing happen. And even when the telescope was not yet completed, he realized that Chicago is not the best place for a telescope, and went ahead to found Mount Wilson, which was the first observatory where they actually really looked for the spot scientifically, looking at weather patterns, seeing conditions, etc. They also paid attention to logistical issues, so that's why it's close to a major city, but back then it was not a real track for light pollution. They looked at Palomar back in the day, but it was deemed to be too far, and so they ended up building things on top of Mount Wilson, the solar observatory first, and then the 60-inch telescope got there. Now the 60-inch telescope is not technically the world's largest telescope of its time, because Lord Rosse's giant telescope was actually larger, because that was 72 inches. Although by the time the 60-inch telescope came to be, that giant was decommissioned. The reason I'm showing it here because I would like to call your attention to the difference which started to show around this time, around the 1900s, that previous mirror-based telescopes were still very, very long. There used to be a day where the greatness of a telescope was measured in its length. So if you see some old graphics from books from like Herschel's age, you know that these telescopes were like, I don't know, really, really long, like 40, 50, 60 yards on big poles with diameters this big, because image quality was of those lenses were not great. It was true for mirrors. They had to make the telescopes relatively slow, large f ratios to keep aberrations at bay and the image enjoyable. But then came the 1900s, and especially a name called Ritchie, we'll talk about in a second, and that resulted in telescopes which started to get wider and less long, which is really advantageous because you can fit it in a dome and protect it from the elements, unlike this one. And as we now know, the more important aspect of a telescope is its diameter, not its focal length, because both the resolution and the light collecting capability depends on the diameter of the mirror. And so I mentioned the name of Ritchie, George Ritchie. You have Ritchie Optical System sitting there, as I hear. And he was really the brilliant man behind the success of the reflecting telescope, the mirror-based telescopes. Because before him, people were making metallic mirrors. And as you know, metallic mirrors don't really have a good thermal behavior. They are not so stable. The temperature changes and then the mirror shape just distorts and the image is horrible. It's also hard to polish them. And so Ritchie was really introduced, he was an optician by trade, and he introduced really, really good manufacturing practices to make optics. And he also was a really ingenious mechanical designer. And he built a telescope which was an F4 telescope, essentially in the 1900s, which was extremely fast, extremely compact, and it made images which were, beating 60, 70-inch telescopes of the time in terms of sharpness and quality. And so it's really thanks to George Ritchie that we have the modern telescope, which is, a fast focal ratio telescope with a tubular, it's not a closed tube, but a tube made out of little tubes to lightweight it. Just for the production of the mirrors, here you can see one of Ritchie's mirror making machines, and you can see that it actually has some protective cover above the mirror all the time, and he required himself and the opticians working on the mirror to wear clean clothes, because he realized that bringing in dust into this environment is going to really damage the mirror, because even those small scratches that you can see by eye cause scattered light and the loss of contrast. And of course he introduced novel concepts for testing the mirrors and making the mirrors, so his contribution to the modern telescopes cannot really be understated. And his design reflects essentially on the 100-inch telescope, which is a really famous telescope, contributed to a lot of the modern science and our picture of the universe today. And this 100-inch telescope, the mirror was done by Ritchie himself, and it was funded. The seed funding came from a Chicago businessman who was dealing with, I think, elevators at the time, and he paid for the primary mirror. But it was George Hale who kind of hooked Mr. Hooker to pay for that mirror because he wanted to, as a wealthy man, build something that will commemorate him even after his departure. And he was debating, well, should it be maybe an 8-inch telescope? But then George Hale just convinced him, no, that's not big enough, because in a few years' time somebody will build a bigger one. So essentially he amped it up to 100-inch. That 100-inch mirror blank was actually really difficult for anybody in the world to make. That mirror blank was so big that I will show you some pictures that even the best glass factories in France could not produce it in one go, because they couldn't produce large enough volume, good quality glass to mold the mirror. So they actually had to melt 3 different batches of glass. But when they layered it on top of each other, the blank became horrible, because as soon as the second layer hit the first one, that melted and some gases got released, and that mirror is full of bubbles, and it's clearly made out of 3 layers. So I'll show you some pictures. And even though that's a horrible mirror, cosmetically, if you look at it from the side or the back, it actually turned out to be a really excellent mirror for astronomy. But that was thanks to Ritchie, who made it to the perfect shape. I'll show you a few pictures of this 100-year-old telescope, because as I will also tell you in a few words, it contributed to modern science quite significantly. And I think it's kind of interesting to look back in time to some of these old telescopes and how they came about, just so we can appreciate what we are doing now. And here you can see the mirror going up on top of Mount Wilson, and especially if you look at the news these days, what's going on in Austin, Texas. The reason why these people are actually walking is not just because they want to make sure that the mirror gets to the top. I mean, they really have not much to do if that mirror starts to tip. They were there because there was a phone call threatening with a bomb attack the day before the mirror left town, because somebody thought that this mirror and this whole big telescope is the work of the devil, and they wanted to stop that. And so a large number of people walked up with the truck just to make sure that there's no terror attack against science there. And it's kind of, really sad to think about it. Even 100 years ago, it was a thing. So here, just a few pictures. I'm not going to talk too much about these. Here you can see how the road was built with literally manpower. And then the dome was built in Chicago, and then disassembled and then shipped to near Pasadena, where Mount Wilson is in California. And yes, those trucks did tip sometime, carrying up those heavy telescope parts, and they had to be rescued with mules and horses. And the mechanics of the 100-inch telescope was actually designed by the at MIT, by an MIT professor in Cambridge, and was built in a shipyard up in New England. Here you can see how they actually very, very carefully and one by one machined the teeth of that worm gear that drove that telescope. And as I said, it was full of really great engineering ideas. The way they supported the huge weight of the telescope, but still made sure that it actually moves very, very smoothly. They did not have hydraulic bearings that time of the day. Many of these telescopes today, they float on high pressure oil, pretty much the same way as big machinery works. They pump oil, and then things just, these tens and tens of tons of structures, they're sliding on very, very thin film of oil. They didn't have that technology back then, but what they came up with is that on both ends of the declination axis of the telescope, they had a big drum, which was surrounded by another drum, and in between the two drums, it was filled with mercury. And essentially, the inner drum was floating in mercury, and that was the bearing. So it was essentially a liquid bearing of mercury on both sides, and therefore the telescope was really, really easy to move, and it was a really, really smooth motion. Here you can see the mirror being cleaned, and here's a close-up shot of the side of the mirror. You can clearly see the 3 layers of glass and all the bubbles. So when Ritchie, as famous optician he was, received the mirror in Pasadena, he refused to work on the mirror, because he said that those bubbles and all that stress logged into that mirror is just going to distort the mirror once it's done. It's not going to give any good image. And so George Hale had to work really, really hard to convince Ritchie to make the mirror, and actually Ritchie told him to quit, and it was not to his liking that he was made to actually finish that mirror. And even to the day of commissioning the telescope, he was stating it's not going to work, it's not going to work. And the funny thing is that when they actually first looked at a star through that telescope's optics, it was horrible. And then Ritchie was like, I told you guys it's not going to work. But it turned out that somebody in the big excitement left the dome open, and the mirror got warm during the day. And that's why it was cooling off, and it was horrible image quality. So they had to wait until like 3 in the morning until it cooled off enough, and then Jupiter was really, really full of details. And then they knew that actually Ritchie knew what he was doing in terms of producing that perfect shape, even though he thought that it's never going to work. Now, the last telescope that George Hale was contributing to, which actually only got completed after his death, was a 200-inch, now it's called the Hale Telescope. From the Rockefeller Foundation, he secured the first huge, significant grant, which allowed to build this telescope, which was the largest telescope for a long time. And beforehand, the 100-inch from 100 years ago, so 1918, to 49, so for over 30 years, that was the biggest telescope. And before we talk a little bit about the Hale telescope, just a few words about the scientific significance of the 100-inch telescope. And so you appreciate actually how much our picture of the universe evolved in 100 years. As I mentioned back then, we did not know how big the universe is. We all the scientists thought that all these little smudges that Massey and others have seen, they are all just little nebulas, part of our own galaxy. They are not too far. Because it's really, really hard to measure distance in astronomy. If you want to talk to somebody who's expert in measuring distance, he's sitting right there, he can tell you how hard it is to measure even just to our neighborhood. But further out, it's a lot harder. And it was not until some actually women astronomers, Henrietta Leavitt, figured out that there are some variable stars where if you measure the period of the brightness change, it actually tells you how bright that star really is. You know the absolute brightness. And as you know, if you have something which has a constant brightness, you take it farther away, it becomes fainter and fainter. And it's a 1 over distance squared law. So if you know the absolute brightness of something and you observe the apparent brightness, you can actually measure its distance. And by measuring variable stars, just measuring the period of their variability, you can get the absolute magnitude, and then comparing it to what you see, you can measure distance. And that was the method that Edwin Hubble used with the 100-inch telescope to measure the distance of M31, the Andromeda galaxy, first. And that's when they learned that, oh, this is actually really, really far. And so essentially the universe, as we know, just essentially inflated in our knowledge. We then realized it's really, millions and millions of times larger than we thought. So the 100-inch telescope had many, many other discoveries. Michelson, that you probably have heard of, about his interferometer, measured the first stellar diameter using the 100-inch telescope, and we could go on and on and on and on. Now, if you have a nice group like you are, you can actually think of once making a trip to California, because the 100-inch telescope was saved by a group of similarly enthusiastic amateur astronomers or hobby astronomers, and now it's refurbished and actually can be rented. Both the 60-inch and the 100-inch telescope can be rented, and you can look through this historic telescope. And I have seen pictures where people take a cell phone, put it to the eyepiece, and they take a color picture of the M57 in just a push of a cell phone down, because that's a big telescope. So keep that in mind. Maybe sometime if you make a group trip to California, you could do that. Now the 200-inch telescope, Hale could not see the finishing of that, because unfortunately Hale had some mental problems which became really, really severe, not to mention that he was suffering of insomnia, which is probably not surprising because he accomplished so much. I mean, he established one of the largest astronomical journals, he established the professional organization of the Astronomical Society, and I could go on how many things he did. And so he died relatively early, couldn't see this telescope to be finished. I'm not going to talk too much about a 200-inch telescope, but I will mention a name. Whose name am I going to mention now? If you look at these drawings, some of you go to Stellarfin and have to know.
Russell Porter.
Yes, Russell Porter, exactly. Because those drawings you see, that was made by essentially a hobby astronomer turned professional. His extreme skills produced all these great drawings, which now we are accustomed to with all this CAD software, this computer-aided design software. We can create any sort of cross-sectional images. But back then, all this engineering was done by hand. And so if you go to Stellarfin, which many of you do, if you haven't been, you should, there you can actually learn a lot more about Russell Porter in amateur telescope making. I'm not going to talk about that now. At the end of the talk a little bit, I will come back to that. But let's talk about telescopes of the modern age, and why are we building larger and larger telescopes. So as I mentioned, the most important parameter of a telescope is its diameter, because the light collecting area scales with the square of the diameter, and the angular resolution is 1 over the diameter. So if you build a larger telescope, you get more light and you can resolve finer details. Now, it's good because a brightness of an object is essentially inversely proportional to its distance squared. So what it means is that if you barely can see an object and you put it twice as far, it's going to be a quarter of that bright, so you're not going to see it. But if you build a twice as big telescope, it's going to have a light collecting area 4 times bigger, and you still see it. So to see farther in the universe, so to say, you need a larger telescope, and to see more details, you need a larger telescope. Now, unfortunately, for every physical object which is three-dimensional, and if it's solid, its weight grows, a cube of its size, and so that's not good because big telescopes then would become really, really impossible to handle. But as I showed you how Ritchie's 24-inch telescope was, Ritchie started to lightweight the telescope and break this law, how the weight of the telescope scales with its diameter. And even today, engineers are working really hard to lightweight things, lightweight the mirror itself, use carbon fiber and other really lightweight materials to enable us to build larger and larger telescopes. Of course, the use of computers helps a lot, but then what we still have to face with is the scaling law of the cost of the telescope. So some of you have your own telescopes, you know that I'm sure everybody looked at bigger telescopes and then looked at the wallet and said, well, maybe not today, because the size of the telescope matters in terms of how much you have to pay for it. And that cost used to scale something like a little bit over the square of the price of the diameter increase. But lately, thanks to again new technologies, the price is coming down. If you're familiar with plane wave instruments, it used to be that a 1 meter telescope used to cost $1.5 million. That was like a rule of thumb. And plane wave kind of broke it into less than half because a meter telescope is about $650,000. And so that's it's not entirely applicable to a 100 meter telescope, but 100 meter telescope costs quite a bit of money. So how much do these things actually cost? Remember this graph from earlier when we talked about size in the vertical axis and then years, how the telescope evolved. Now actually I can replace that number on the left to dollars. And that kind of tells you what's the cost of these telescopes. So you can see that the largest telescopes that people are thinking of and actually building already, these 24 to 40 meter telescopes, they are around the $1 billion mark. Now, what is $1 billion? For us sitting here, I think all of us, it's a lot of money. And so the reason for that is probably obvious why it costs that much, and we'll talk about that a little bit later. But what I would like to call your attention to is that this figure can be divided into like 3 regimes. There is, I'm sorry, the colors are probably not showing up too well, but there's this regime which a single individual can pay for, essentially. And then there's this regime of like, going from like maybe $250,000 to up to $100 million, where large institutions, universities, or countries can pay for. But then when you reach this $1 billion mark, not even Harvard, the richest university out there, I guess, can afford that by itself. And even single countries cannot afford it, because even if they could, they spend it on F-35 fighter jets and other toys. It's kind of interesting that an F-35 fighter jet is about, what, $250 million? So you need only 4 to build the largest telescopes, and the government ordered 2,500. So probably you could spend it just 4 of the price for a large telescope. But at the moment, the US government is not paying into any of these large telescopes, which is interesting. There is such a thing called the National Science Foundation, the NSF. The NSF pays $0 to the development of any of these ground-based telescopes. Don't get me wrong, the NSF pays for a lot of things, like the LIGO, the Gravitational Wave Observatory. They put about $2 billion over 3 decades, and that's great. But there's, very little money for science these days, especially these days. And so, unfortunately, it's up to private donors and private institutions, at least in the United States. Now, I say here in the United States because now I'm going to talk a little bit about politics, not politics of today, but politics of the past century. Because it's very, very interesting that if you look into the history of telescopes, for hundreds of years, Europe was leading the charge of scientific discovery and building good and large telescopes. But what happened just right around the time when George Hale came about to build these large telescopes, essentially the lead of astronomy moved from Europe to the US. And there came something called the First World War, and there came something called the Second World War, and Europe never really recovered from those. And even though the US was part of those endeavors a little bit, but it affected its economy much, much less. And so from about the late 1800s to just about 20 years ago, the US was leading. And if you recall this graph, I had like individual names attached to these points because many of these telescopes were financed by a single wealthy individual. And that only happened in the US because in Europe there was not a single individual who remained wealthy after world wars. And Europe, when it kind of woke up after the Second World War, they kind of realized that, oh, if we want to compete with the US scientifically, we can't really beat that without collaborating. And the first really big scientific collaboration Europe did was CERN, the particle physics research facility. And now the Large Hadron Collider is actually really outdoing any of the US facilities. But it didn't happen overnight. It's a highly bureaucratic organization with, couple dozen partner countries and a huge budget and lots of scientific politics involved. But they kind of figured out how to work that. And a second similar organization came to be also in the 70s, was called ESO, the European Southern Observatory. And right now the most productive facility, maybe not owning the largest telescopes, but the VLT, the Very Large Telescope, which is only 8-meter telescope, but there's 4 of them. And even though the Keck telescopes, which is again was paid by the private individual, Mr. Keck, even though those are larger, and there's 2 of them, but the 4 VLTs are actually producing a lot more scientific paper than the Keck telescopes do. And out of these 3 dots at the end, these extremely large telescopes, the largest one is the European one, and the other 2 is the US based. But as I will show you, the problem with those US based that the government is not backing that up. And I will jump back into that little bit of geo and scientific politics in a second. But before we go there, here's another law that you probably all of you know, that's called Moore's Law, which shows how the computational power of the devices that we have evolved over time from the punch card to essentially very, very crude electronic devices to those smartphones which could outdo a computer of 20 years ago in less than a heartbeat. They show a similar trend that over time technology is steadily evolving and allows us to do more and more science. And so if you translate that to astronomy, it translates into ever larger telescopes, as I showed you in that graph, and also translates to more science. Here on this graph, again, you see time, and you see here it's just a number, and so the quantity shown is different. You can see, for example, how many galaxies per year can people survey these days. And so obviously the scientific output, the number of discoveries, increases linearly with how many objects are we studying. And so thanks to the ever larger telescopes, the ever larger computational capacity, which is coming to very, very heavy play in today's science, you can see that the number of galaxies that we are monitoring, surveying, researching is very, very steadily increasing. So the science of today is very different than the science of 100 years ago because now we are dealing with very, very massive amounts of data. And so very often these days scientific research is not entirely tied to a single telescope, but there are survey telescopes, which I will talk about, which will produce data that will be analyzed and mined for decades to come. So the landscape is a little bit different now these days. So I'm going to talk about a little bit about the Giant Magellan Telescope. Here is a oh yeah, there we go. So this is just a computer-generated video of how the giant Magellan Telescope will look like when it's fully built in Chile. And you can kind of gauge the size of that building as the virtual camera kind of moves around, and you will see some equipment on the ground. Those are cars parking there, over there.
How are they going to keep it clean? I mean, it's in a dusty desert.
So Chile is actually much less dusty than many other places. The Canary Islands, where some other big telescopes are, it's much, much worse because dust from the Sahara actually gets there. Chile, the Atacama Desert is very, very clean, surprisingly clean. And humidity is very, very low. And because of that, even if there's some dust, it doesn't really stick to the mirror surface that bad. So now this giant Magellan Telescope, which is the smallest of the extremely large telescopes, is a partnership between all of these institutions. It's led by the Carnegie Observatories in Pasadena, and the Carnegie Observatories essentially was established by Mr. Carnegie, a wealthy individual who was supporting the build of Mount Wilson at the first place, and it's still a very active player. It's joined by the University of Arizona, Texas, universities, Chicago, there is Harvard, the Smithsonian Astrophysical Observatory, but besides those US institutions, we have partners in Chile, because it's going to go into Chile, and so the Chilean government and their educational institutions are partners. The Australians and the South Koreans are in it, because, again, this is about $1 billion telescope, and none of those above mentioned institutions can put that money down. Matter of fact, only about the half of the money is available at the moment, even with this many number of partners, and so the future of this telescope, as well as others, is a little bit uncertain. And that's where I a little bit lash back to that politics, because the reason how the Europeans kind of took over very, very slowly, at least in astronomy, but also in particle physics, is because they figured out that they have to be able to work together to create something really, really big. And so in the US, where wealth was abundant, at least compared to the war devastated Europe, it never really happened. Individual people, individual institutions could manage. But now, as you can see, this many number of institutions, even with international partners, is struggling to come up with $1 billion. Versus the European Southern Observatory have a very different scheme, because very early on they decided we're going to do something big, we're going to make a partnership, but every member has a member fee. And so it's one thing to actually build a telescope, which is going to cost you $1 billion, but over 10 years of operation, it's going to probably cost you another $1 billion, because there's so many things that have to be kept up. And so it's not enough just to build a telescope, you have to operate it. And the US, institutions who are partners for the GMT or the TMT, they are struggling to find the money for building it. Nobody's talking about how they're going to operate it. In Europe, ESO is actually secured 90% of the money for the building telescope. They don't have it physically, but since they have partnership agreements, they know the money is going to come. And they also know that for operation, the money is going to come. So we'll see, of course, how it all plays out. At the moment, the GMT and the European telescope is going ahead. As you probably have heard, the TMT had troubles because on Hawaii, the natives kind of prohibited putting up yet another telescope. But the latest court ruling, I think, is in favor of the astronomers, so they can probably proceed. And so I'm at MIT at the moment. I used to be at Smithsonian. MIT is not a partner institution yet, but hopefully we will become partners as well. I was working on some of the instrumentation of the Giant Magellan Telescope in my previous job, not since I moved to MIT 4 years ago. But MIT is still a better place. I like it. If you ever come and visit. So here is just a few pictures of how the GMT is proceeding. Here's the mountaintop, Las Campanas. It means bell in Spanish, because the rocks have such a high iron content that if you pick up two pieces of rocks and you kind of cling it together, it really, really rings like a bell. And so the mountaintop looks very different. They blasted off the top. They made roads. They started to put up support buildings. Now the support buildings are in place, actually, so the work crew can live there. And what the GMT did is actually they built their mirrors. If you recall some of those pictures earlier, the GMT is different because instead of using hundreds of hexagonal segments for the mirrors, it only uses 7 segments, but those 7 segments are 8.5 meters in diameter, so very, very large. And it's a fundamental difference how to build telescopes. This is probably the largest mirror that humans at the moment can build. As you can see, this is a relatively thick mirror. Some of the mirrors, like the VLT mirrors, they're also 8 meters in diameter, but they're only this thick, about 6 inches. Those mirrors are not self-supportive. They're like a piece of paper. When you hold them underneath, they will just droop down. So in order to make an 8.5 meter mirror like the VLT work, you have to support it with many, many, many supporting points, several hundred. And each of those support points actually are actively driven. So you can shape the mirror to that perfect shape that you want. That's one way of doing it, but it increases system complexity because you have to know all of those actuators every time to a fraction of a thousandth of an inch where they are. Whereas these mirrors, which I will show you in a second how they are made, they are very, very thick, and so they are self-supportive for most of the time. And so they are much easier to deal with once they are built. Now, of course, a big chunk of glass like this would be so heavy that the telescope would require to be also very, very heavy and robust. So in order to lightweight it, maybe many of you are familiar with this technique, but they build a honeycomb structure. And as you can see, they are using these hexagonal columns that they all cover, and they leave tiny, tiny little gap in between, just about an inch wide. And the complete honeycomb structure, as you can see here, is essentially just very, very small volume between these hexagonal columns. They put lots and lots of glass on top. And then once they filled it with glass, they build an oven around it. And this is a special oven which can actually spin, because the surface of the mirror, as you know, is like a deep dish. And so if they would just melt the glass and let it to cool flat, they would have to grind a lot of material out, which is a lot of time. So what they do is actually they spin cast, because as you spin a liquid, it takes up that perfect paraboloid shape on the surface. So they built a furnace which was the brainchild of Roger Angel at the University of Arizona. It's underneath the stadium of the Whitecats, and that's where they make these big mirrors. And then the finished product looks like this, and it's lightweighted to about less than 20% based on its volume. So it's a very neat trick, and the GMT would consist of 7 of these segments. And again, for scale, that's like a personal vehicle, like a car, and that's like a big semi. So we're talking about big telescopes.
Yeah.
This is how the site looks like. I took this image, I think last year, from the Magellan telescopes, which are 6.5 meter telescope. This is the residencia where the astronomers and the support group sleeps, and you can see that's the Las Campanas peak. With some star trails, and overnight they put it up. That's how it would look like, probably to scale on that mountaintop, a couple of miles away.
Excuse me. My understanding is the GMT is going to be the first telescope that doesn't have star pattern, doesn't have the
well, it's not going to have central obscuration, the ones that we are all accustomed to in these tubes, because due to this structure, whatever is holding the secondary mirror here, those support rods are going to be in between these mirrors. But still, the central segment is going to have some of the obscuration. So it's going to have, but the diffraction pattern that we are used to these crosses, that cross is coming from the secondary mirror holder. But diffraction itself is also coming from the edge of the mirror. So the diffraction pattern of this is going to be really ugly. It's going to be, it's going to be a central star, nice and sharp, but it's going to be surrounded by a hexagonal pattern of ever-fading dots. So it's going to have some diffractional pattern, but not the one we are accustomed to.
Okay.
So here you can see, in comparison, some of the largest telescopes of today compared to, say, a tennis or a basketball court. It's March Madness, so let's compare it to a basketball court.
That's European basketball.
Say again?
That's a European basketball club.
Yeah, I told you I'm from Europe. Sorry.
The web picture.
So here you can see the Keck telescopes up there, which were the first telescopes really pioneering the hexagonal segmented mirrors. And here you can see the VLT, the Very Large Telescope, which is 4 separate telescopes, but one of the instruments that you just recently commissioned, called Espresso, of course it was named by the Italians, combines the light from all 4 mirrors together. So actually it became really the very largest telescope in terms of light collecting power. And so here you can see what the GMT will look like. This circle is the effective aperture in terms of light collecting area. And this is the 30-meter telescope. And this is the EELT, which has about 1,000 segments of 1.8 meters across. And so now let's talk about these different mirrors. Oh, here, you can Google it up. I told you that Pasadena is the home of the Carnegie Observatories, which is the lead institution in the GMT. So very optimistically, you can go into Google Earth or Google Maps, type in Carnegie Observatory, zoom in the parking lot, they painted up the outline of the telescope. So you can see it's big. All right. So this is how a current large telescope, a 6.5 meter Magellan Telescope, scales the GMT or the EELT. And again, these are fundamental different telescopes because of the mirror support structure. So let's talk about the technologies and the economy of multiplication that plays into role. So here you can see that GMT is 7 segments and the EELT is 800 segments of 1.4 meter in size. So in astronomy, when we make larger and larger telescopes, of course, it's useful to just reuse technologies that are developed by the industry. So one of the really key ingredients is finite element analysis, which is allowing us to design structures and predict their behavior under different conditions, thermal conditions, mechanical loads. This is key to develop airplanes, and here you can see a movie of telescopes dancing, because the telescope under its own weight will deform. And so if you're holding optics respect to each other with high precision, but the whole structure just droops on its own weight, that alignment is going to go really bad. And so these finite element analysis tools allow us to predict how it's going to be, so we can stiffen up the structure, use different materials to make sure that this alignment doesn't happen. And of course, we have to be careful because wind, even though there is an enclosure around it, the wind can blow the telescope and that can start resonating, and then the stars will just wobble back and forth. So there's lots of very, very tricky engineering going into these mirrors, into these telescopes, where we can just lift technologies developed by other industrial entities. However, there are technologies that nowhere else exist. And mirror making is one of those. And so here you can see, I'm not sure who that picture is, my apologies. Now I'm really curious myself. This was Telefin on the left, obviously, where they had a mirror making demonstration. I think that picture was like 7 or 8 years ago. But so these technologies are very, very unique. And so if we want to produce ever larger mirrors, we have to evolve those technologies ourselves. Nobody wants mirrors that smooth that we want. But we can drive some of the industry, like Zeiss, to produce machines which are computer controlled to generate those perfect mirrors. However, when you're trying to scale it up to the size of an 8.5 meter mirror, there is a person there, then it becomes really tricky. And I like to give this example because, yes, it's a very, very smooth mirror, and I can say to this crowd that, oh, that shape has to be perfect within a quarter of the wavelength, and you know what a wavelength is. It's about, for visible light, it's about 600 nanometers, so we're talking about 150 nanometers, but what is 150 nanometers really? So here you can see a surface map of that mirror, where the color is coding the deviation vertically from the perfect surface. Wherever it's red, it means it's too high. Whenever it's dark blue, it means it's too low compared to this ideal surface, which would focus starlight into a single point. So now here's the scale. So between the blue, which you can call 0, the largest deviation would be 1/1000th of the width of your hair. Everybody can pull the hair now. Look at it. It's really tiny. Divided by 1,000, it's tiny. So that kind of gives you a scale. But still, I like to give this example. Excuse me, I'm from Massachusetts again. And so here is a topographical map of Massachusetts. The low-lying areas in the coastline, and there are some mountains out in the west. And it's kind of using the similar color scheme. Red is high, blue is low. And so you can guess, if I say that, let's assume that Massachusetts have been polished like a mirror. How tall would be the tallest point in Massachusetts? It would be approaching a perfect flat, as well as a mirror does. Again, just as a comparison, Mount Greylock is about 3,000 feet. So how tall Mount Greylock would be, you think?
6 inches.
Okay, so here, a quarter of an inch. Okay, so imagine whole Massachusetts being as flat that nothing is taller than a quarter of an inch. So if you blow up a mirror of a telescope to the size of Massachusetts, it would be as flat. So it's really, really amazing what our opticians and engineers achieve making these mirrors. And even I said that this is a self-supporting mirror, it's just partially true, because even on the back side of this mirror, we are using about 120 actuators to actually make sure that that surface is really exactly, because once you start it tipping over, actually gravity changes and the shape changes. And so even a mirror like this is complicated. If you look at one of those actuators, it has many moving components and encoders and whatevers. But if you look at some of these segmented mirror technologies, then you have to keep in mind that a single segment like this has like a Wiffle tree, which means it has 3 active components with everything multiplied by probably 6 or 9 passive components, and that you multiply by 800, and you realize that a big mirror like what the EELT is planning is a highly complex system, and it's computationally very intensive to keep it where it needs to be. Now I am at 57 minutes almost, and I have only 50 slides left. So I will hurry up. No, I don't have 50, but I still have like 15. So I will just showcase a few key technologies which are really important for these big telescopes, and then I will close up with some comments about smaller telescopes after talking about large telescopes. So seeing is believing, and so the problem is that there are F-35 fighter jets. I think that's a problem. But the problem, what I'm trying to illuminate is that, as you know, if there's a hot gas somewhere, which is essentially just the Earth's surface, which warms up during the day, and a hot gas rises up, but it does rise up in a turbulent motion, which is the very same thing what happens if you look through some exhaust fumes of, for example, a fighter jet. The vision gets blurred because the light passes through that turbulent air. It just essentially zigzags around, and it will make an image of a star that's mushy and changing. However, the image of a star should be like that. That's your eerie pattern. That's what you want in a perfect telescope. But it's not like that. And so now we can make this come into this, because that's an actual movie made by a so-called adaptive optics system. Because what people can do is we can measure the distortion of the atmosphere as light passes through. What we do is light comes from the telescope and we split it into 2 halves. We take the visible part and we put it in something called a wavefront sensor, which can tell us how badly the light is distorted. And that is coupled back through some really super fast computer to a mirror, which is actually deformable. We have many actuators, and 1,000 times a second we can change its shape. And the atmosphere is not changing as fast, so the atmosphere is changing maybe 100 times a second. So what we can do is we can make the shape of this mirror the complete opposite of what the atmosphere is doing. And so therefore, whatever we're recording on our camera becomes from this really dancing around mushy thing into this very, very sharp stuff. And so that adaptive optics is going to be a key component for these giant telescopes, because the larger the telescope is, the more sensitive it is to atmospheric distortion, because the characteristic size of these atmospheric turbulent cells is about 20 centimeters or 8 inches. And so the larger the telescope is, the larger number of these cells are in the path of where the telescope is looking. And so the more horrible the image becomes. So here's an 8-meter telescope without adaptive optics looking at a star cluster. And that would be an 8-meter telescope of today. That's an actual image, not a simulation, what it does with adaptive optics. Now you can say, oh, but why don't we go to space? And we take like the James Webb Space Telescope, which is hopefully going to go on its way, and it's going to be even better. Yes, but the James Webb is about going to be $8 or $9 billion by the time it flows to space and works, hopefully. If something goes wrong, you cannot fix it because they're going to put in a Lagrange point. So let's hope nothing breaks. But to that I say, if you build a 25-meter telescope and put adaptive optics on it, which is going to cost you $1 billion, 8 times less than James Webb, that's what you get with adaptive optics. Okay, so adaptive optics is really going to be a key component to these large telescopes. And adaptive optics is really cool because very often it uses a laser system to measure that wavefront, so you can take cool images. This is several years ago from Arizona at the 6.5-meter Mmt Telescope. And so just a couple of images of these deformable mirrors. These are very, very thin glass shells, about maybe 1/16 of an inch thick glass piece, which have many magnetically driven actuators underneath, and that's how we can generate that shape and change it 1,000 times a second.
How do you get the laser light back? You send it off into space. How does it come?
So we don't send it to space. What we do is the atmosphere has a layer which is really rich in sodium, up about 90 kilometers height from the ground, and the laser beam is focused with a small telescope to 90 kilometers. And there it excites those sodium atoms, and you generate an artificial star. And that just shines light every direction, and some of that comes back to the Earth. And that's high enough that most of the turbulence in the atmosphere happens way below that. So when that scatter light comes back, it carries the same signature, which distorts the image of the star.
So you really only need to look at one wavelength? Or the excitation wavelengths of sodium?
Yes, so that's enough. Right. The problem is the field of view, and so these AO systems at the moment are limited in field of view, but they're working on putting multiple guide stars. But it's a really complicated issue. Okay. So we talked very, very briefly about space telescopes, because as we all know, space is the final frontier, to some, not to everybody. But the reason, again, we go to space, because if you look at wavelength, where this is visible light, this is infrared, this is radio, and this is ultraviolet and X-rays. This is the transmission of the atmosphere, which means, sorry, not the transmission, the absorption of the atmosphere. Which means when it's 100%, it means nothing is coming down. And it's good that no UV radiation is coming down, because otherwise our skin would be really, really bad. Visible light comes down, some of the infrared, and a lot of the radio. This is called the radio window. But so if you want to go to space, why you want to go to space? Because from space, essentially, it's just a flat line at zero. You can see every wavelength. And that's important because when you're trying to look at an astronomical phenomena, it's really helpful to see what happens at different wavelengths, because if something is very, very hot, it mostly emits radiation over here. If something is very, very cold, it's mostly emitting radiation over there. So you can figure out the physical processes. If you are a birder, you can actually understand why the ultraviolet or other wavelengths are important, because some birds you cannot distinguish the female and the male, unless you would have a UV glass or UV binocular, because in a UV binocular, actually, you can quite strikingly see differences between male and female of the same species. So it's kind of the same thing. That's why you want to go to space, because you want to be able to observe the different wavelength regimes. But again, as I mentioned, space is expensive. It costs a lot of money, and you can do quite well, actually, from the ground with some of these adaptive optic systems. I'm going to skip that for sake of time and just talk about what I mentioned earlier, is that since we are producing these extremely large CCD cameras with gazillions of pixels and telescopes with meters in size, you all know about the LSST, the Large Synoptic Survey Telescope, which is going to scan the entire visible sky every third day, and it's going to produce 30 terabytes per night data, and so essentially thousands of astronomers can be fed with all that data and keep busy, years at end to figure out all these variable sources which we never even dreamed about. So astronomy is also moving, thanks to these big telescopes and the extra computational power, into a little bit of a different territory. Here's a big CCD compared to a person and compared to the field of view in the sky shown by that moon in there. That's the LSST CCD. That's a big one. You don't want to process those images on your home computer. And so the ground-based advantage again is the size. We can build much bigger telescopes here, so we can still collect more light. We can access them. We can actually build instruments to them, fix them when they break, and then we can do lots and lots of cool things even from the ground. And as I said, I have many slides left, so I'm just going to skip over them. I was going to talk about some instruments and just point out that in the old days of like 20 years ago, a telescope used to cost $10 to $40 million. These days, the instruments cost that much, because the bigger the telescope is, the bigger the instrument needs to be proportionally. And so these systems that I am building and designing, they're as complex as telescopes used to be. And of course, we are doing spectroscopy, where we are spreading the light out and analyzing all those spectral lines to look for chemical signatures, measuring velocities, and all sorts of things. And the interesting thing is, once you have a big telescope, you want to actually multiplex its power to harvest more. So you could put a single detector on a big telescope, but that's not good. What we are doing is, we are doing science fiction in a way that we are using Starbucks. So those are Starbucks from the movies. That's not what we do, even though it's horrible, I know. But these are little piezoelectric driven fibers. On a big telescope, an image would be like literally this big. Instead of trying to put many instruments on the telescope, what we do is we only put tiny fibers, and those fibers can walk on the glass plate. Those are called the Starbucks by this piezoelectric motor. And then the fibers run into remote spectrographs where we can have hundreds of them. And so this way we can multiplex the power of the telescope, because we can actually observe hundreds of objects at the same time. We don't have to do it one at a time. And of course, we are still doing space-based surveys, because some of the things you can only do from space. And the reason I'm showing some of these exoplanet transits that probably you're all well familiar with, these are the transit surveys where an orbiting body crosses in front of its host star, obscures some of the surface, and the brightness of the star measured vertically over time diminishes and then returns. That's how most of the exosolar planets are discovered these days, many by the Kepler Space Telescope. But now there's a new kid in town called TESS, the Transiting Exoplanet Survey Satellite, which was built by MIT. That's why I'm showing it. And the reason why it's going to do really good, because Kepler, that I'm sure you all heard many good things about, Kepler only observed this tiny portion of the sky compared to the whole sky. And TESS is going to do a 24 by 90 degree scan for 30 days. And every 30 days is going to turn. So it's going to scan the full hemisphere 1 year, and then turn around and do the other hemisphere. It's going to do a full sky survey with the same quality observations what Kepler did. And even though TESS has only 4 tiny telescopes, about this big, those are very expensive and very big telescopes that I worked on at MIT to put together. Here are some lab pictures when we are putting them together and testing them. And so just to show you again in an example of what the sensitivity of those telescopes are, is if you imagine your telescope is in San Diego and you are looking at the lighthouse back in Boston, if a moth flies in front of that lighthouse, that's about, and you're looking at 4,000 miles away, that's about Jupiter crossing in front of a star. And this annoying sun a mosquito is about equivalent of how much the light of that really, really bright spotlight of a lighthouse diminishes when a mosquito flies in front of it. It's the same if an Earth-sized planet crosses in front of its host star. So can you imagine seeing a mosquito flying in front of a lighthouse 4,000 miles away? Now that's hard. That's how hard it is to measure these transits. And the atmosphere is so bothering to these measurements that for this we essentially have to go to space. So there is that, and I'm gonna close up on these technological things with something which is called the radial velocity surveys. You probably all know about the Doppler effect, which modifies sound of a moving object. When the train comes, it's a high-pitched sound, and it goes, it's a low-pitched sound. The same thing happens to light. When a body is orbiting around a star, it's not the body orbiting around the star, but because the body has mass too, so essentially they're both orbiting the common point of gravity. And so the star wobbles a little bit. And so when you're looking at a spectrum of a star, you see the pitch of the light changing due to the Doppler effect. And you can measure this change. So here, again, it looks easy on that figure. Can you tell me? It's a movie. So if you zoom into one of those lines, that's moving. I'm not kidding you, this is a movie. I can give you the file and you can see it's an MPEG movie playing.
Jeez.
But you don't see it because the motion is 1/10,000th of a single pixel. So how do you measure that? Well, the reason they're able to measure that because you measure thousands of lines at the same time. But again, we're talking about measurements which are very, 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 very small changes in order to measure the mass of these objects. And the reason I wanted to show you this because the only way you can measure it if you have some really, really highly stable fiducials which can be compared to the positions of those lines. And I'm not going to go into too much detail how we create these fiducials. They have something to do with lasers. But the interesting thing is that these so-called laser frequency combs that are providing us this ruler against which we can measure the Doppler shift of stars at the speed of walking of a few meters per second.
Wow.
Is generated by optics which are about a micron in diameter. Again, your hair is about 100 micron. So again, it's a honeycomb structure suspended 1 micron diameter glass rod which can generate this really, really crazy ruler. So the funny thing about astronomy is it's using the largest pieces of glass and the smallest pieces of glass together to measure these exostellar planets. And these exostellar planets, again, is something we don't fully understand how they formed, but hopefully we will soon know, thanks to, again, ever larger telescopes like ALMA, because it's not just the optical, as I said, but also the radio, the ultraviolet X-rays, where we have to build bigger and bigger telescopes. I'm going to close up on going back in size from these giant telescopes, because this is an image of what telescope? Everybody's Hubble. This is an image of what?
The pillars of creation.
No, this is an image of this telescope.
Oh, really?
Yes, and the fact is that we probably don't realize, because we get accustomed to that we can just take a digital camera and a telescope and we can take an image like this. It was not like that. I don't know how many of you have hypersensitized film in hydrogen gas in a vacuum canister. I did that too. And back in the early 90s, there was this thing called the CCD camera cookbook by Richard Berry, where you would build a detector, which was not a camera, which used a detector for like 200 by 150 pixels. And so people who are turning into astronomy these days, and the young generation, they are used to these things. And it's awesome, and it's really hard to see that the professional astronomers of just a generation ago have not had access to the quality of data that we can do now. I mean, God forbid, we can see exoplanet transits with telescopes of this size from our backyard because we know how to do it. So it's a really, really amazing technological advancement which happened over the past decade. So you go to NEAF, and then you can just, I want to buy that and that, or if you have more money, I can just buy that. And then you can actually do a lot of things with it, which scientists, university professors were doing just in your parents' generation. And so it's really, really amazing. But at the same time, no matter how amazing that is, I still urge you to go to stellophane because that's really amazing in a different way. Because you can build telescopes out of plumbing supplies. You can build, I mean, this is a funny one, I admit, it's sort of not that useful, but it actually still makes an image, and it was a funny telescope from last year's stellophane. And so you can use a pizza box in more than one way, and you can, create some really elaborate instruments if you put the time into it. So the point is that even though I talk about these giant telescopes, which are going to pop up on those, really far away mountaintops, I think the message is that you want to take away is that those are cool, but those are not for everybody. And no matter what size and what make of telescopes you have, just go and get out under the night sky and look through the eyepiece and take your own images, because the personal connection is the most important, even for us who build those big telescopes. And on that note, in 1 hour and 15 minutes, thank you for your attention.
Thank you.
Questions?
You showed the spectra of light that gets blocked by the atmosphere, and you have to be up in space to see UV.
Yeah.
My understanding is the Hubble's the only UV telescope up there right now. And is there any?
There are others.
There are? Okay.
Yeah, well, there are more X-ray telescopes at the moment, but there is at least one more. But the Hubble is highly capable, although it doesn't go far in the UV, because the detectors
Right.
are not really made for it.
That's a
Yes.
tough. Detectors in UV is tough.
Yes. I'm happy to answer questions. I know you're all exhausted. Sorry again for talking too long. Thanks for sticking it out. And I do have to get back to Boston because I have a flight at 6 a.m. tomorrow. But I'm happy to answer questions if you have questions, so you don't have to rush out.
Why did the MMT go to a single mirror from a double mirror?
So they back in the day they were not able to make 6.5 meter mirrors. But they started the experiment with these honeycomb light-weighted mirror structures, and the first ones they built were 1.5 meters. And so they were like, oh, so how can we build a large telescope? They were not having enough money to build a large furnace, and so they said, oh, why don't we just put it on a common mount and try to combine the light? But it turned out it was actually more difficult than they thought. And that's why when they were not able to combine images sufficiently of those 6 large mirrors, when Roger Angel decided that, okay, let's just build one big mirror, and they developed the technology. At the same time, in California, another group decided, well, let's go the other way, because we think those individual segments actually do work. It's just, and yeah, they both made it work. Jerry Nelson pioneered the Keck telescopes, and yeah, they are building them.
Wow.
Are you going to be involved in the launch of the TESS telescope?
Yes, so the reason we originally had this little bit of a swap of the date, because the original launch date for TESS was scheduled for today, but then there were some technical mishaps, and so right now it's scheduled to no earlier than April 16th. They have a launch window of 40 seconds every day for about a week, and then after that there's another launch coming up in the West Coast, and if they miss that, unfortunately they have to get congressional approval to launch it, because it's going to cost some more money. So hopefully it will launches, and yeah, I will be involved because I was involved in the building of the cameras and testing the cameras. So I
Where
would
is
like
it going to
to.
launch from?
It's gonna go from Florida. Yep.
What's the rocket?
It's a SpaceX Falcon 9. But this one is not gonna have the return because it's a moon synchronous orbit, so they have to push the spacecraft really far. So they will try to catch the rocket by a barge far out in sea. So it will be not that spectacular of coming a rocket or 2 rockets back. But
Still pretty
it
exciting.
will be a pretty launch. So hopefully, my son who plays these computer games of like Kerbal Space Program and Space Engineers, maybe some of you know, he's really excited to watch a launch for real. So we are going there.
Congratulations.
Thank you.
How many pixels in the camera?
For the TESS, so TESS has 4 telescopes. Each telescope has 4 CCDs, and each CCD is a 2K by 2K device. So essentially it's a 4K by 4K, so 16 megapixel camera. and it has 4 telescopes.
And their fields of view overlap.
No, they don't overlap. They are individual because they're 24 degrees apart. So there's a little bit of a gap between. But since the instrument will rotate 30 degrees at a time, the one which is looking at the pole, that will just observe the same field over and over and over again. So there we will have a long data series. Near the equator, we will only have 30 days for each star. So there we will only see short period planets, because you need multiple detections to confirm. On the pole, we can see longer period planets.
What's the aperture of the test individual telescope?
Those telescopes are about 5 inches in diameter, f1.4 focal ratio, fast.
1.4.
Well, they are really fast and they're really wide fields. So,
Yeah.
What are the pixel size on the?
So the pixel size is physically it's 15 micron and it's about 40 arc seconds on the sky. So it's going to be a crowded field, meaning there are going to be multiple sources per pixel. So if they see a source which is varying, they have to follow them up by ground-based telescopes where they can split them up and make sure what that is.
Mm-hmm.
Why wouldn't you have used a higher resolution CCD than that?
Because you have to process the data and you have to downlink it, and there are
So
resources.
transfer time and
Well,
resources?
yes, you have to manage the resources because the test orbit is such that it's a moon synchronous orbit, but it's like a half moon period. It's an elliptical orbit. It goes really far out and then comes very close to the Earth. And then there's a short downlink period where you have to push all the data and then it goes.
Wow.
And so they have to optimize all sorts of resources.
One of the properties of CCDs when you're doing exposure is to prevent the pixels from blooming.
Yeah.
My understanding is that there's just a little bit of a wobble put into the telescope to keep that from happening, or is there some other trick?
On CCDs that hobby astronomers buy, there is a so-called anti-blooming. Essentially, it's a wire trap system on the surface of the CCD which captures those bleeding charges. There's no such thing because that decreases sensitivity.
Right.
So there, bright stars will saturate and flow. They do build a special CCD architecture to kind of combat that to the extent they can. And the spacecraft itself will have a jitter. Every spacecraft have a little jitter. But given how big the telescopes are in angular size, it's not going to be that significant. And so there are going to be saturated stars and they just have to deal with it in post-processing. And some of those saturated stars cannot be used.
I thought I'd seen a picture where one of the telescopes was space telescopes actually had a nutation to it to keep that to a minimum.
Yeah, but that's that's different. That's for a reason, as I understand it, is to actually keep the pointing stable.
Okay.
Because it's easier to make a motion which is constant than no motion at all whatsoever.
Are the sensors monochrome or color?
It's monochrome. This one has a single filter. It's a 600 nanometer to 1000 nanometer passband. So red and near infrared. There's no moving parts. Moving parts are bad. Bad in space.
That's great.
Really nice.
All right. Thank you.